So Philippe is from the French National Center for Research. He's working there as an engineer since 2005, in particular at the Magnetic Resonance Center for Biological Systems, where he's in charge of the experimental and instrumental development at low magnetic fields. And he's in particular involved in the development of the Overhauser enhanced magnetic resonance imaging approach with the use of the dynamic nuclear polarization at 0.2 Tesla, which is quite low, which has led actually to this European-funded project, Primo Gaia, together with Professor Jean-Michel Franconi and other partners, including industries that are distributed in different European countries. And today, Philippe will present the status and the results of this project. The floor is yours, Philippe.
Oh, thank you very much. Thank you all for being here, and thank you for the Euro-BioImaging to invite me to this talk. I hope you hear me correctly. Let's tell me if there is any problems. The presentation will mainly talk about development and result of the Primo Gaia project, which is part of the H2020 program and the FET Open dedicated programs. I will try to explain our work in Overhauser enhanced MRI imaging, and I will do also some explanation of the physical principle behind in a simple way for those who are not familiar with OMRI. So let's start in detail. And the base of this story is, I'm sorry, something is that we were looking at what we can do exploring low field MRI. We know now, and mainly now, because a lot of high field systems are worldwide developed, and it's a very nice and good tool and efficient tool for medical application and diagnosis, because it has very efficient SNR and resolution versus times and many other applications. But it's also expensive, high technology. And what to do with low field? Nothing so much, except some exception with the hyperfin project. Only marginal medical application, but because the first limitation comes from its low intrinsic polarization. But in the other hand, it cost-effective technology, mainly with when using permanent magnets. So let's try what we do here. Just what can we do with low field MRI? One way to overcome the low intrinsic polarization is to use the OMRI to boost this polarization via interaction between electrons and protons. Using this, we can get a good signal improvement and new contrast. As drawback is it becomes more complex because it's a double resonance system with a conventional NMR system with frequency depending on the field. And the new ESR, that means electron spin resonance, RF channel, to be able to irradiate the electron transition. In the other way, with the help of contrast agent, it could help you to discover new contrast and to approach the specificity of contrast to a pathology or anything else. Back to the principle of OMRI, or dynamical nuclear polarization, sorry. When you have a mixed spin population in a liquid state, for example, or in tissue, and you have some coupling between electron spins and proton spins. If you irradiate by a proper irradiation frequency, the spin transition of the electron and saturates this transition, by this coupling, there is a transfer of magnetization then from the electron polarization to the proton polarization. This is translated by a high enhancement of the NMR signals, and we'll show in detail how it works. And how can we do this? We have not so much unpaired electron available in the body, so we need a contrast agent. There are a lot of contrast agents available on the marketplace, and they are mainly the nitroxide family. And these molecules have a coupling between nitrogen and the unpaired electron. So that means this coupling will generate 3 different transitions that are available at high field. By measuring this electron spectra with an EPR system, we can measure the coupling expressed in frequency. It's about 40 megahertz for this kind of molecule. So this is one coupling system giving 3 lines or 3 transition to access for electron saturation. In details, these 3 lines are specific transition, and it's typical of what we call the SK system with 2 spin numbers, 1/2 for the electron and 1 for the nitrogen proton. And this gives us with the effective dipolar coupling between electrons and between the base molecules and the surrounding water protons, a max DNP factor of 110. With a minus sign because this polarization works against the magnetic polarization from the applied field. We can use other more complex molecules. We have a collaboration with the ICR in Marseille. And with these people, we develop a double couplet system with coupling with nitrogen and coupling with phosphor. And in this case, it comes up with 2 coupling constants here measured on the EPR spectrometer. And you can see how this coupling constant expressed from this spectrum. And the coupling constant from the phosphor is greater than the one from nitrogen. It's about 100 megahertz against 40 megahertz. And it gives us at high field 3 lines, 3 different transitions we can irradiate for MRI. And in final, when we irradiate 1 transition, we will get a maximum of 55 enhancement factor, again with a minus sign. And a lot of work has been done at our lab since the beginning of MRI in 2003, that was initiated by Jean-Michel Franconi and Eric Thiaudière. And a lot of people had been working on this, many doctorants, and actually Darman Boudries is working with us on the new system. Some of the results from this 0.2 Tesla system application of MRI, at 0.2 Tesla, which is a low field for MRI, it's quite high field for OMRI because the electron transition will be saturated in the gigahertz range for 5.4 gigahertz precisely. And this is really high, and this gives some heat. We take some precaution. We need a special cavity to propagate with microwave and to avoid any heating in the middle where the sample is. On the left side, you can see the result from in vitro experiment using a small tube of nitroxide within a larger tube of water. And you see when the electron spin resonance frequency is on, there is an enhancement of the inner tube with the nitroxide at 1.35 millimolar. The gain was about 25. And we get it also in 3D with microtubes at 5 millimolar. We get a gain of about 40, which is a really high gain. And going into the mice model, the gain are not so important, but still quite interesting because while injecting a non-toxic nitroxide in the blood system of the mouse, we get in the cranial area enhancement about 10 in the vascular system and about 2 in a vascularized tumor. At the bottom, you can see the natural image from MRI at the same field, 0.2 Tesla. And going more deep with this kind of contrast agent, we can, when we leak to via some molecular construction to a bigger system like BSR systems, we get a nitroxide BSR linked system with a slow motion. When there is slow motion, there is less exchange with water protons. So when you look into the APR spectrum, you get the black flat spectra. That means no gain with DNP or MRI. If the system is digested by proteolysis and with pancreatic proteases, then the nitroxide gets free again with a fast tumbling. And this gives back the line, fine line for the APR spectra. And we can show in red on the APR spectra. At the bottom left, you can see the announcement of the image in a tube in vitro activity for measuring the enzymatic activity. On the right side, we can see the application after oral gavage in mouse. We can see at the duodenum announcement of about 6 due to the pancreatic proteases. This is the first enzymatic OMRI image we have done in Bordeaux. Another application was using this 6-line nitroxide, again with some enzymatic activity here with neutrophil elastase. We can change the conformation of the initial molecule to change its signature that can be seen on the APR spectra. And you can see under the red arrow that this is the product after digestion. This is a ketone form, and the substrate under the blue arrow, this is the enol form. And this change in signature is translated into OMRI at 0.2 Tesla with a change of irradiating frequency for the ESR and with a shift of 8 megahertz. And when we set 2 tubes of the different either product and substrate, we can irradiate one or the other depending on the irradiating frequency and gives a result with OMRI at the bottom here. So now we go back to the Primogea project, which was our main subject now. We started still end of 2019. And this Primogea project is built with 7 partners coming from 4 different countries. There are 5 research labs and 2 industrial. Industrial are Pure Device in Germany. They are make a lot of electronics for NMR systems. And Stella in Italy, they are known for building field and cycling fields. CNRS is doing the coordination, and we have under WP3 package for contrast agent, we have a free university of Mons in Belgium, Aix-Marseille with the ICR lab in France, and the University of Torino in Italy. The project was originally on 42 months. It has been extended for 6 months due to COVID restriction. Behind this project, what is the ideas? We have done some experiment on high field system. That means 0.2 Tesla for us in OMRI is a quite high field system. And with non-invasive in vivo diagnostic tools. There are still developments for contrast agent, and this will take long time. But we need to investigate what could be application for larger field of view in the aim to target body exploration, for example. We know already that the technology is available. It's a cost-effective technology because it will implement low field, and it could answer to new contrast. And the aim of this project is also to know the real limitation of such a project, and this is a pre-project to investigate this problem. The main problem is that using microwave technology like at 0.2 Tesla is not possible for whole body examination because microwave is heating. It is known from each one because when you have a microwave oven in your kitchen, you know that it could heat up water. And the other question is what happens with the ESR irradiation when we get down to a very low field. We know already some theory about this, but not all is known. The wavelength problem appears already at 3 Tesla systems, but 3 Tesla system is 128 megahertz. In the air, it's a wavelength of 2.3 meters larger than the field of view of the imaging system. That's okay. But when you go to water or human tissue, then the permittivity effect results in a wavelength of 1/4 meter. That means the size of the human head. And you have already inhomogeneities visible in B1 in the human head that has been corrected on medical system, but you have also more even in the body for this kind of examination. They need to be corrected. And thus our problem is this point, how to do OMRI within whole body systems. We know already that it's not possible at 0.2 Tesla, so we move and explore the ultra low field domain. First field we explore what was the Earth field, and we built up an open system on a low-cost project from Carl Michaels, and we implement on it an RF channel for ESR excitation. And from this first experiment, we end up to the project Primo Gaia, and still in the ultra-low field domain, but with the frequency, SR frequency in the range of 4 to 150 megahertz. The idea behind the project is, I said already, the technology is there, and we will need 2 RF channels, one for electron speed resonance, one for the NMR. Let's say if we work at about 200 microtesla, and with EPR or ESR, it will be about 150 megahertz. We'll see later on why. And for the NMR frequency, it's known to be about 9 kilohertz. And we need also gradient. This is easy to build because we will need only less than 1 millitesla per meter. What we need is preparation of the sample, because the natural polarization at ultra-low field is very weak below the noise level, so you cannot measure it directly. You need to accumulate for hours or use preparation. You can use a magnetic preparation with a prepolarization for about 20 millitesla, for example, prior to the NMR acquisition. Then the initial magnetization, this will be the magnetization due to this 20 millitesla field. And these are the solution on the system we use now. It's called the first kernel system because it's dedicated to small animal imaging with a field of view of about 10 centimeters. So we need, we have from left to right a birdcage coil for ESR, solenoid for NMR reception and transmission, a gradient coil, and a prepolarization coil with cooling to be able to do in vivo application with temperature regulated experiments. What's missing at the moment is we need also some approach and theoretical calculation for the nitroxide coupling at ultra-low field. This is well known for the free-line nitroxide, but when you get 2 coupling in the SKP systems, we need some digital simulation and calculation with matrix operators. And we can initiate this calculation from the molecule properties measured in the EPR spectrum. What is known is that when going to low field, the Zeeman effect disappears or is less dominant, and the coupling effect is predominant. And it ends up only with 1 transition frequency nearly, which is 3/2 of the coupling constants. Coupling constant is about 40 megahertz. That means the frequency will be about 70 megahertz. But it's not enough to know this. We have to go further in details. And going to ultra-low field, it has been shown also that not only P transition are available, but in P transition is one are available when B1 is perpendicular to B0, but we can also have sigma transition available when B1 is aligned with B0. But you can see at high field already at 10 millitesla, only the P transition remains. There are free transition, there are the free lines we know already from the EPR spectrum. And the sigma transition are only available at very low field, below 2 millitesla. And we won't use it so much because our first experiment showed that it was not very efficient anyway. What happens at low field? It's also that transitions are not of the same sign. Some are positive enhancements, some gives negative enhancement. And these are very close in frequency. And if you irradiate the SR frequency with linear polarization, we get the sum of the two effects. And you get, as shown on the right, you get a net polarization that is not very efficient. With a null point at the middle. If you use circular polarization, you can irradiate either the positive wave or the negative wave and get much more enhancement. But don't look too much. So the enhancement factor, they are very great, but maybe it's not enough. And what about the SKP system and the free line? I know there is no analytic solution. We have to calculate a few computer calculation. This has been done by Elodie Parzi in our team. And based on the Hamiltonian, which is a 12 by 12 matrix, we can calculate the different transition and DNP factor for each transition available for DNP. And to predict the signal enhancement we can have on images. Here are some results of this calculation from the B0 effect. On the right, using the same calculation, you get the theoretical transition for the free line systems, because I use it because it's more simple with 6 lines, so it's better to explain it with the free line systems. So you see the free transition around 5.4 gigahertz. On the left side, with the same calculation for 200 microtesla and 45 microtesla. In the thin lines are the 45 microtesla. They are very close to each other, and you have in blue the sigma transition and in red the P transition. And if we increase slightly the field, we can see that the lines are splitting, and the thick lines, red and blue, shows P and sigma transition for 206 microtesla. The result when exploring different fields is this. There is a big difference between circular polarization and linear polarization, depending on the field. That very low field, there is a huge difference, but when going to higher field, its max DNP factor seems to be lower. There is not so much difference because of the splitting of the different transition. And so we may explore this area of the field because it may be interesting for us. You will see later. And we look to the normalized scenario when we take into account not only the enhancement factor, but also the intrinsic polarization from the field. We can see that at 200 microtesla, the attended signal is much better than what we could attend from 45 or 50 microtesla. This is the reason why we choose this field to work with DNP, because we can work it in simple way with linear polarization, and there will be no difference from linear to circular polarization. Now we can go to the result. When we know the theoretical basics, we can go to the result of this project. We have one first result at the beginning of the project using the Earth field NMR setup at 45 microtesla. We'll see an application of we previously see in the theory, and after we get the first system from the consortium. We call it the first kernel setup. I saw it already as some solution, a technical solution we implement in it. and we use it for small animal imaging. And we want to use MRI on living animals and to do some targeted contrast with azymatic activities. The last step that will come to at the end of the year is the MRI feasibility with the whole body system. I will talk about it at the end. What we need when using ultra low field, that means with polarization field below 1 millitesla, we need a preparation step because the intrinsic polarization is not enough. So this preparation can be magnetic with a higher field and or dynamic with a ESR irradiation for OMRI. And this happens prior to the NMR acquisition. In between, there may be some switching time due to the technique. And here on the right, a simple description of pulse FID sequence using this kind of preparation for both magnetic and dynamic. The first setup, the Earth field NMR setup, was this. It was a low-cost system developed by Carl Michaels, an open system we build up here in Bordeaux, and we implement on it an ESR RF channel to be able to do dynamical polarization. All on this system, all has to be aligned with the Earth field. It was about 45 microtesla in Bordeaux, and the P1 for ESR coil and MR coil should be perpendicular to the Earth field, so it needs some precaution and north orientations. On the top right, bottom right, you can see the ESR coil we used. So we did some experiments using the contrast agent we had at this moment and measuring an enzymatic activity with the 6-line nitroxide at 45 microtesla. And this enzymatic activity is translated by a change in signature from the substrate, that means the enol form, to the ketone form. And so we first measure the DNP spectrum of the ketone form to be able to target the correct frequency for the DNP experiment. This is shown on the right side here. You see the problematic of the two antagonist polarization, positive and negative, and the curve of the measurement done at 45 microtesla. So we target this ESR frequency at 150 megahertz, and we monitor this, the signal during the enzymatic activity, starting from the substrate plus where we added enzyme, and monitor with pulse FID measurements up to the end of the digestion and obtaining 100% of ketone form. You can see the curve here within 200 minutes. And now we're working on small animals with the first kernel systems. It's a complete system with imaging and 2 consoles made by Pure Device for MRI and ESR, and all complete system, gradient system, and we'll show that in details in the next slides. This is the examination area of the system. You can see the sample in the middle tube assembly. And the first step we get is the ESR coil, because this is the birdcage coil. And since the NMR coil, which comes after, is a fixed solenoid coil, it may shield the ESR frequency. So this is the reason why the ESR coil is inside. After the NMR coil, we get the prepolarization coil that needs for magnetic prepolarization and natural standard contrast. And the external system is the gradient coil system. And in between, you have aluminum shielding to avoid any frequency interference from line supply. Typical low field NMR pickup coil. It's made of selenide. The middle one is a signal selenide. That means the sample is put it inside this coil, and this coil is a gradiometer configuration. That means there are two coils. One is measuring the signal and the other is measuring nothing. And both are sensitive to external noise. And that means the second one is connected opposite to the first one receiving the signal. So when you add it together, you get 100% for the signal and zero from the external noise. This is ideally, in practice, it may be not the same. Here, due to symmetry, we split up the noise coil in two parts, but this is equilibrated to function properly. We built up also a dedicated preparation coil for in vivo imaging with thermal regulation to be able to do rat imaging without any problems and any overheating of the rat, because as you can see, the external temperature can go very high. And this coil gives a homogeneous field on 80 millimeter for field of view. What we do when we use magnetic prepared MRI, we need to boost the polarization by the preparation field. This is done by a solenoid in the same direction as B1 NMR. That means there is a transition between the preparation and the NMR, and this has to be adiabatic, that means slow enough that the polarization can follow the field transition and be aligned with the final B0 transition when doing the NMR. B0 here is the range of 200 microtesla. This is a result on a small phantom with different frames to show the proper encoding of the image. And you can see that for 2D, it's okay. It's about acquisition time of 5 minutes with a good contrast. But trying to do 3D, due to the preparation time, it took a lot of times. It's more than 2 hours, nearly 3 hours for 3D imaging. With this will be not compatible with what we want to do for MRI, for example. And so what is the MRI specificity? We can use it as previously for magnetic preparation. That means preparation with with an ESR excitation of the proper frequency, and then the second step with MRI acquisition, and then cycle through TR like this. But if you want to gain in time, because time is SNR, we may change and do continuous irradiation, doing some precaution on RF path and shielding. We can continuously irradiate the electron spin resonance while acquiring the MRI signal. This is shown on the right drawing here. That means that the field will never change, will be at constant field. That means using linear polarization with a field of more than 200 microtesla. The result is this. You have 3 orthogonal fields. The two B1 fields are orthogonal to each other and orthogonal to B0. And you can see on the bottom right, birdcage coil used for rat for MRI. And a reminder for the theory, at 200 microtesla, we get a good DNP factor, and with no difference nearly between the linear and circular, so we can use linear polarization. This is the result we get first in vitro. We want to know the level of the threshold of detection for the concentration of nitroxide. And here you can see that 0.1 millimeter is detectable in 3D imaging with enough resolution for this system. That means 4 millimeter in the plane and 8 millimeter in slice. This is done with continuous irradiation, ESR irradiation, with a 3D balance steady state free precision sequence. And the irradiation was done at about 72 megahertz with a free line natroxine easily available. You can see that water tube, they give no signal because there's no interaction, electron-proton interactions. This is another test to see the profile of OMRI in the other direction on the same kind of tubes, 1 milliliter vials at the same frequency. And we can see even in 3 millimeter resolution in plane and 6 millimeter in slice, we can see the enhancement emerging from the noise. One interesting point on this technique at ultra-low field, with ultra-low field, but only the signal coming from this interaction, electron spin resonance to proton resonance, will emerge from the noise on the image. There will be no signal from magnetic polarization. Going to in vivo, the main problem is that we don't get enough data from laxivity of tissue, of living tissue mainly. And what we get from the data comparing standard high field magnet like 1.5 Tesla to lower field, but the T1 and T2 are going down, except for water or pure liquids. And we will deal with short T1 and short T2. That means mainly below 100 milliseconds. We try to do some measurement on the wall rat. It's not really a measurement because the T1 is of a wall rat is not really a parameter, but we end up with T1 of 180 milliseconds and the T2 for 94 milliseconds. So to be able to do image in vivo with the system, we need to change the sequence paradigm. And we test different sequences, and the one that was most efficient was the zero echo time sequence called ZTE here. That is the shortest readout of signal. The time between the pulse and the first point of acquisition is about 13 milliseconds. It is the shortest time we can get at this field. It's nothing compared to high field equal time. There is no comparison possible. And the total TR is about 250 milliseconds. And so we can go quite fast doing acquisition and 3D acquisition at 206 microtesla. This is one result of the ZTE. With 3 millimeters resolution, you can see that we get a better SNR with this sequence than the previous BSSFP sequence for the same parameters within about 1 quarter, 13 minutes exactly. So to summarize, we will use ZTE either for magnetic polarization or for MRI imaging for in vivo, and we can use still standard spin echo sequence with magnetic polarization of or balanced SFP sequence for continuous irradiation for MRI. The frequency we choose is selected from our contrast agent that is about 72 megahertz. And these are the results we get on rat imaging. The rat model is shown on the left, and different organs we image this here. On the first OMRI image, you can see 3 spots, two red and 1 green. This is the two kidneys that are visible and a little bit of the bladder, which was a little bit outside of the FOV. The central polarized image is a setup of 3 different acquisitions of 30 minutes each, made with magnetic polarization. And the right MRI image is done on pulmonary systems. We can see enhancement in the lung after instillation of a non-toxic nitroxide agent. And the image on the kidney, on the bladders were obtained after intravenous injection of top-car nitroxides. And it's clearly visible. And when we look later on, after 20 minutes after injection or 20 minutes after installation, we can see that nitroxide is accumulating in the bladder, showing that this kind of contrast agent is clearly and fast eliminated by the body. This was already known from previous experiments at 0.2 Tesla. So the last step that will come within this project will be the whole body project. It's already under test being integrated in Germany at pure device location. It will consist of a large system body compatible for the preparation, the B0 cage, gradient system, and the transmit NMR coil. For the receiving part, solenoid for whole body will be difficult to build and maybe not a solution. So we go down to a smaller size with a head size, receive an MR gradiometer coil, and for the ESR coil, we did also head-sized coil. Together, this is a RF channel for whole body has been built at a small company here in Bordeaux. It will deliver 3 kilowatts in continuous wave and 10 kilowatts peak. This is already valid for whole body ESR coil. We will use lower power for the head coil for sure. So I would like to thank all participants to the Primagaia project and also all previous participants from MRI experiment at Point to Tesla. From the CRMSB, I would like to thank Elodie Parzi for his theoretical contribution and Cedar Seren and Daman Boudries for the experimental work on the small first kernel systems. I would like to thank you all for your attention and all the members of the consortium of Primagaia too. So thank you for your attention.